All right, let's look at this problem here. If 12 grams of brass at 5 degrees C is added to 24 grams of water at 30 degrees C, what will the equilibrium temperature be? And I give you the specific heat of the brass. So let's sort of examine for a minute what's really going on here. I have a sample of brass that's cooler than a sample of water, and I'm putting the brass in the water. So imagine that. I've got a beaker maybe with 24 grams of water, and I've got a chunk of brass at 12, that weighs 12 grams at 5 degrees starting temperature, and I put the brass in the water. You would think that those two temperatures are eventually going to be the same. The water cools down, the brass heats up, and that's exactly what happens. Now, the way that happens is that the energy in the brass, due to its temperature, is being increased. So this is going to go up, and the temperature of the water is going to go down. And the amount of the energy change, not the temperatures, but the amount of the energy change is going to be the same. That's how you're going to reach that equilibrium temperature. Okay? So let's take a look. All right? That's how we figure that out. Let's plug in what this Q is going to break out to. So Q, as long as you're only changing temperature, is going to be equal to the mass times specific heat times the change in temperature for whatever that species or substance is. Well, the water also has a Q, and its mass times specific heat times change in temperature. The equation for calculating Q, as long as you don't go through a phase change, is the same. Mass, specific heat, change in temperature. If you go into a phase change, it's a different equation. Mass times change in enthalpy, delta H. But right here we're only going through those. Now, it's important to recognize that temperature change is always temperature final minus temperature initial. Delta T is temperature final minus temperature initial. And the temperature final here will be the equilibrium temperature, the point at which the temperature of the water equals that of the brass. So T sub F is the same for both water and brass. Okay? So let's plug all that in. So for the delta T term, we're putting in this. Okay? TF minus TI. TF minus TI. Now, the final temperature is the same for both water and brass, so I'm not going to put an identifier here because TF is the same for both. But the temperature initial is going to be different for the brass than it is for the water. Okay? All right. So we're going to plug in all our numbers now. So there's 12 grams of brass. The specific heat of the brass is 0.380 joules per gram per degree C. That was stated here. Temperature final minus temperature initial. The initial temperature of the brass is 5.0 degrees C. Then negative, for this negative here, negative the 24 grams of water, the specific heat of water, which you must memorize. Temperature final minus temperature initial. The initial temperature is 30 degrees C. It says so in the problem. Okay? All right, then. We need to distribute now. Let's talk about what this distribution of terms means here. If I have something like this, where I have A times B plus C, the A is distributed to the B and the C. So A times B plus C is AB plus AC. Now if I have two multipliers here, A times B times C plus D, then the A and B both get distributed to the B and the D. So A times B times C plus A times B times D. That's what I have here. A times B times C plus A times B plus C. Now if we're subtracting here instead of adding, okay, then it's still distributed, only you have a minus sign in between. A times B times C minus A times B times D. And that's what we have over here. A times B times C minus A times B times D. Okay, so that's what we're going to be doing here. We're going to be taking this term and multiplying times this, then subtracting this times this times this, and the same on the other side. This times this times this times this times this minus this times that. Okay? And that's what we're doing to both sides. And we do that, then we get all of this. Okay? So 12 times 0.380 times TF, we get this number with these units, grams, joules, T sub F over grams times degrees C. That's what we have here. And you can cancel out the grams then. minus this times this gives you this number. You have grams, joules, degrees C times grams over grams times degrees C, or divided by degrees C as well. And you can see you can cancel out the grams and the degrees C. Over on the other side, this times this minus this times this gives you this stuff. The negative here is also distributed in the same way, so that this negative times this times this and this is positive, so this negative makes it negative, and this then you have a minus this times this, the negative terms distributed to make it positive. So a negative times a positive is a negative times a negative is a positive. Now then I can cancel out units over here as well. I can see that I have here in this term joules TF degrees C, and over on here I have joules TF degrees C. And what I want to do now is to collect terms to get these two terms over on one side, this side for example, and there's only joules left here and here, so I want to collect all those terms on the other side of the equality statement. So to do that, I'm going to subtract this amount from both sides. I'm sorry, I'm going to add. It's a minus term. We're going to add this term to both sides to get rid of this term, and add this term to both sides to get rid of this term on this side and move it to the other side. This is how it works. Okay, I'm adding that 100.32 joules TF degrees C, 100.32 joules times TF degrees C here, adding it to both sides. Okay, they're both right here. And I'm going to add this term, 22.8 joules, to both sides. And what that's going to allow me to do then is to get 104.88 joules TF degrees C on this side and 3,032.4 joules on the right side. Now, to get rid of everything on this side but TF, because that's what I'm trying to find, the final temperature, I'm simply going to multiply by the reciprocal of everything else remaining, 104.88 joules over degrees C, multiplied by the inverse, the flip of that part of the fraction there. Okay? And that's what I have here. Degrees C is on top, 104.88 joules that's here on the bottom. So what that's going to do is cancel out all this. Degrees C cancels, the number cancels, joules cancel, I'm left with TF by itself. So if I do it to this side, I've got to do it to this side. And you notice this term here is the same as it is here. And by doing that, I also cancel out joules on this side. Okay? And then I'm only left with degrees C, and degrees C will measure a final temperature. Degrees C is a measurement of temperature. And I get this number. So here's our unrounded answer. You go back to the entire problem, carefully examine how many significant digits you have. You'll eventually see that this is the overriding factor in determining significant digits in the final answer. When you do the multiplication across everything and the addition and subtraction across the entire thing, you'll see that you'll have a final number of significant digits, or should have a final number of significant digits of 2 significant digits, like this one, 1, 2. And so here we're going to round off everything but the first 2 digits. So we're going to underline starting with a 9 to show all those digits are insignificant, and that's required, and then use an arrow to show that we're rounding off to this number. And that's our final measurement of temperature. Now, is that reasonable? That's a question you need to ask yourself about any calculated answer. Is it reasonable? Well, let's go back to the original problem up here, and let's take a look at the numbers we put in. We started out with double the amount of water as compared to brass. We also have more than 10 times the amount of specific heat for the water than we do with the brass. So both of those weights this problem toward the water. That's one way to think about it. So the temperature, our final temperature, should be closer to that of water than it is for brass. Further, the temperature needs to be in between this 5 degrees C and that 30 degrees C. Okay? So 5 degrees C and 30 degrees C has to be in between there because it is an equilibrium temperature. Somewhere has to be somewhere in between. So this is indeed somewhere in between and much closer to the original temperature for the water. The original temperature of the water was 30 degrees. And so for those 2 reasons, this seems at least a reasonable answer.